And now, without any further delay, I would like to introduce you to today's presenter, Mr. Tom Groff. Tom Groff's professional education includes a degree in aerospace engineering from Embry-Riddle Aeronautical University, as well as an MBA with an emphasis in technology management from the University of Phoenix. Tom also holds a black belt certification in a Lean Six Sigma. And now, without any further delay, I'd like to hand it over to our presenter. Tom, you now have the floor.
Thank you very much, Melanie. Welcome, everybody, to the webinar. Today's webinar is going to be concentrating on how multi-sensor metrology can cut manufacturing costs. So we're going to delve into the depths of all the different sensors that a measurement system can have and how, at the end of the day, that affects your bottom line. As you can all probably appreciate, there's been several advancements in medical device manufacturing, and I'm kind of proud to say that it's improving the way we all live. With the baby boomers and whatnot, everybody is getting new knees and new hips and ear implants and hearing aids and dental implants. You can see some of the devices that are going into today's bodies, and it's just a crazy thought to think that 20 years ago none of this was happening. So it's all interesting technology, but it also offers several challenges to manufacturers and people that are doing measurement on these medical devices. The manufacturers are challenged with complex shapes and structures. The human body is not made up of prismatic features like cylinders and planes. It's all of these very curved surfaces, and that's always a difficult thing to handle. Also dealing with having to manufacture smaller parts to fit into some of these smaller cavities and areas. And also tighter tolerances, so that's always a challenge to manufacture and measure to tighter tolerances. So what does that mean for us? Well, with all of these complex shapes and no real, the conventional geometries that we're measuring, requires complex fitting, complex GD&T, geometric dimensioning and tolerancing criteria to be able to make sure that these fit correctly into the body. And of course, that feeds down into the measurement. The science of measurement is metrology, and the metrology of medical devices can be very complex. But there are ways, or there are solutions out there. So this is a knee that you're looking at here. This is kind of a interesting picture. Trying to measure that knee with conventional measurement tools can be somewhat challenging, and I'm sure some of you out there have experienced these challenges. It's unrealistic to expect to measure these kinds of parts with conventional means. So what are the solutions? That's the topic of today's discussion. So this is a video of a multi-sensing system, just to prelude the presentation with the solution. It's basically using a combination of sensors: a video sensor, a scanning probe, a touch probe, a laser, and it's incorporated into a 3-axis measurement system with 4th and 5th axis capability to rotate the part underneath the sensor. So there it was doing some video measurements. You can also see in this video that there's some scanning going on the surfaces. So this is scanning an unknown contour to try to define the characteristics of that part. These programs that are created to measure these parts can be created automatically to a known part or to unknown parts. So this one in particular was basically defining start and end points. And then at the end of the day, you can get a color map, a whisker plot, a GD&T report. All of these different things are able to be reported out to help you understand, what the actual part looks like relative to the nominal part. So how do we solve this challenge? There's several ways to do it, and we're going to talk about basically the resolution to these challenges. So we have sensor technologies that we're going to talk about today. We have software solutions that complement the sensors and that make the sensors work, and that also creates the kinds of reports and information for companies to make good decisions. But also relative to the medical industry specifically is compliance, accuracy, and compliance to standards and FDA requirements. All of those things come into a multi-sensing measurement solution, to where it's not just the technology that's provided, but it's the accessories and the services and things like that can help you have a full-blown solution right away. So let's start with the sensor technology. Several sensors are out there, and we're going to talk about quite a few of them today. And, so if we look at the different sensors, we have kind of a scary-looking picture there. I saw that somewhere and thought it was a perfect thing to define, the senses. So what is the definition of a sensor? It's a device that receives and responds to a signal or a stimulus. And that's really what all of these sensors are in a multi-sensing measurement system. When you think about human senses, you think about touch, feel, taste, hearing. Really this picture here kind of represents the touch and the seeing, okay? And that's really what we concentrate on when we're measuring something. We need to touch it and we need to see it to be able to define these dimensional characteristics. So we're going to talk about all these sensors listed here. We have some video sensors, we have probing sensors, different kinds of lasers that can scan a part, scanning probe you saw in the original video there. And then we have some more unique sensors relative to another tactile probe that resonates, a white light scanning sensor, a non-contact scanner, a fiber probe for very small parts, and also thermal sensors. So let's elaborate on some of these. First, we're going to talk about optical and video technology. The core of what Optical Gauge Products, which is who I work for, does is all of their systems are equipped with a video sensor as the base unit, and then you can add on sensors to it. And there's some significant technology involved in the way that you grab video, and maintaining the metrology aspects of that is very important when you're talking about a measurement system that measures down to the microns. So we have different kinds of tools that we use with video. We have filtered edge finders. The image in the upper right corner is a grid projector that projects a false image into the optical path so that you can do autofocuses. We have pattern recognition, finding maximum points, scanning over unknown contours. If you look at the lower right image, the yellow dots there are points that it found on that kind of contoured edge. When you're talking about video technology, you're really measuring the image. So it's important that the image is accurate, because you're not actually touching the part, you're imaging it. So the lighting comes into play there. You need good lighting, all that kind of stuff. Also, conventional measurement systems, like maybe a CMM or something, you're measuring surfaces. With video, and it's sometimes good, sometimes bad, it measures the area where surfaces intersect, or where it sees change in contrast. And that is typically desired as you're measuring the actual part, and where these surfaces may interface is where these measurements need to be taken. So, this next video is a quick demonstration of just video technology in general. So let's take a look at that. What this is going to show you is how some of the sensors are used. So here it's doing some edge detection with all the green points on there are points that it's finding on the edge, scanning around this unknown contour towards the back of that part. So you're talking about thousands of data points as it's acquiring, and then you can compare that to a model or create dimensions out of it. Here you're seeing different lighting characteristics also, backlight, surface light, light coming from different directions, and then here's some pattern recognition on the letters there on that part. So just a few examples of the way that's applied. Let's move on to the next sensor, tactile probing. This is pretty well known out there. It's been in the industry for a while, and it offers some flexibility in the way that you can measure things on internal surfaces or around on, for the example in the lower right corner, that indentation, measuring the location of that or the size of it by actually going in and touching the part. So what this uses typically is kind of a strain gauge technology where when that probe is triggered, it senses that point, takes the XYZ data point there, and then you can create different geometries and information from that. It does do single point acquisition, so you're moving this XYZ stage on a measurement system, and the points, the probe is actually contacting the part one point at a time. It's good for measuring geometric surfaces. So like I said before, video is used to measure edges where surfaces intersect, and this is more for measuring surfaces like cylinders and planes and things like that. So let's look at this next video, a quick example of touch probe measurement. So here's a touch probe coming in to measure this circle or the cylinder on the part. So it's actually coming in and approaching the part. As it senses the touch, it backs off. Another example is a very small part. You can get down with this conventional kind of probe down to about 0.5, 0.3 millimeters, something like that. So this is a very small probe on that small gear mechanism, kind of setting up a datum on that gear. And these probes can be put away and docked and picked up, with different stylized sizes and orientations. So in that respect, they're pretty flexible. Okay. The next sensor we're going to talk about is similar to a touch probe, but it's actually going to maintain contact with the surface as it measures. So instead of taking single points, it's scanning over the surface. And the technology behind this is basically a pivoting mechanism on an isolated optical system to measure the deflection. So instead of strain gauges or something, it has an internal optical system that measures that deflection. So this is ideal for contoured surfaces. If you want to take a lot of data points on a surface and map it out, create a large point cloud to compare against a CAD model, those kinds of applications, that's where this comes into play. What happens is it scans at a constant force, and as it detects the deflection, it will actually change the servo direction to keep the probe at a constant deflection away from the part. So let's take a look at that. This is a video of a scanning probe scanning around the exterior of this black part. So you can see how it maintains a constant deflection. This is a little model window of the simulation of it, and that's how it's used to help program it. Scans at relatively high speed. That was kind of an XY contour scan, but you can also scan over surfaces, in the XYZ kinds of orientation. And this is scanning over the top of this small contour. It's extracting that arc out of that slot. Okay, the next sensing technology that we're going to talk about is same kind of probe, sticking with the tactile theme. This is a more unique probe for measuring either very small parts or flexible parts. So when you have the other conventional probes, they typically require some magnitude of force on the part, and in some cases that just can't happen, or it's undesirable. So this technology uses resonance. So this probe is hanging down and it's actually resonating at this optimum frequency. And as it approaches a part, that frequency changes and immediately a trigger or a point is detected. And so it senses that change in modulation, and that's how it triggers that XYZ point. So you can, a typical probe is typically 1 millimeter to 5 millimeter stylus size. These probes can get down to about 100 micron as a stylus tip. So very small parts in that case. The probing forces on a typical probe is typically 0.06 newtons or something like that. The contact force on this can be as low as 1 milligram. So it's these other kind of sensors are really good for addressing specific applications that conventional measurements sensors do not. So let's take a look at the feather probe. This is a very small hole. Example of a small hole shows the penny there as a reference to the size. So let's take a look at this video. The advantage here that you have a multi-sensing system is that you can actually measure something with video, non-contact, like it's measuring this hole here, and roughly find out where it's located, and then come in with a very small diali and know that you're going to go right down inside that hole, as opposed to if that's off a little bit of location, a very small hole like that, you have the potential of hitting that probe on the surface before you go down into it. So here it's taking several points around that diameter of that very small hole. That's a 250 micron hole and a 125 micron tip that was used in that demonstration. The next sensor that we're going to talk about is sometimes referred to as an interposer or a fiber probe, and this is a pretty cool technology. It actually incorporates a couple of different sensors into one. So what it does is it has typically a very small probe used for, again, small kinds of features, or features that are kind of indentations, internal recessed features, and things like that. And that black little symbol up there represents a video camera. So you're looking at this tip, and as it's dragging along the surface, you're measuring the tip with a video. And then it's compensated to kind of project onto the surface. So let's look at an example of that. This is a 45 micron shaft with an 80 micron tip measuring a 300 micron hole. So basically you see the probe is hanging down. That is right at the focal plane of the optical system. So that dark dot that you see there is the probe tip, and it's focused right at the depth of focus of the optical system, and then it's using those edge finders to locate it. So it moves the stage until the probe touches the surface, and then it measures that tip with the edge finder and projects the radial value onto the surface, and that's how you make those measurements. So kind of a unique sensor, but it certainly fits the bill in some applications where you have very small features or recessed features that nothing else can measure it. Okay, let's talk about lasers now. We kind of went the gauntlet with tactile sensors, or sensors that actually touch the part. The advantage of having a non-contact sensor like laser or video is you can probably guess some of the advantages. You're not contacting the part. There's no damage to the part for very sensitive materials. There's no chance of it deflecting or moving when you're doing a non-contact thing. So Laser sensors themselves are good for measuring surfaces with non-contact. They're very high resolution, very high accuracy sensors, and typically have their highest level of accuracy in the Z orientation or normal to the path of the laser. One technology relative to lasers is called triangulation, and the concept here is that a laser emits a beam onto a surface, and that beam is then reflected off of the surface into a detector of some sort, and that detector senses where the beam is hitting. There's typically a spot associated with the laser beam that you can see in the upper right graphic, the red spot there. As that moves back and forth on the sensor, that indicates a delta Z down in the lower left, and that's how you determine the Z location of where the sensor is at. So it's a pretty interesting way of making very high accuracy Z measurements. There's a couple different ways that triangulation is applied. There is off-axis triangulation. We have this standalone laser head. That kind of red box there has an internal laser to it, so this can be added onto a measurement system, or sometimes they're standalone by themselves, just scanning very high accurate traces or very small features, and sometimes they're incorporated into a online system for online measurement. The TTL laser on the right stands for through the lens, and it basically sends down that beam through the optical system, the same optical system that's used for video measurement. So there's some advantages to that. You get typically a little bit more working distance, and you also have no offset associated with the video to the laser. So in other words, they're at the same XYZ location when you're measuring features on one part with both sensors. For the off-axis lasers, we calibrate that offset out because you have the optical path at one location and you have the laser path at another location, and as long as we know that offset, we can calibrate that out and maintain a coordinate system on a single part. Okay, let's talk about another kind of laser technology, interferometry. This is a relatively new and innovative form of laser. It's not a new concept, really, because interferometry has been used, for years for calibrating very high accuracy devices such as gauge blocks, and they've been used in, in the physics environment. But basically, this is relatively new, incorporating into a measurement system with multiple sensors. So relatively the same concept as the triangulation laser. It goes through the front lens of the receiving optics, the same optics that the video uses. But instead of triangulation, it uses interferometry. And what that means is that it superimposes two or more wavefronts on top of each other to detect the changes in Z. So the distance is determined by the difference between those wavefronts. And the advantage here is that typically there's a physics a conflict that we as measurement system developers have had relative to making a multi-sensing system versatile enough to have a long working distance and still maintain a very high level of accuracy. Because typically when your accuracy goes up, your working distance goes down, which makes it a little bit less flexible to work with. This technology actually kind of breaks that barrier. So now we have the ability to have a long working distance and still get down to micron levels of accuracy. So you can get up to 200 millimeters of working distance, and in other words, the distance away from the part that you're measuring, and still maintain that kind of accuracy. So it's just it's great technology. The other advantage of it is that it can measure right next to a vertical wall. So with triangulation, sometimes if a beam is headed downward and there's some blockage associated with a fixture or the wall on the part, it gets blocked and you're not able to measure right next to the wall. So this comes straight down and straight back up, which is a huge advantage. So this is a very flexible laser. It has the same level of accuracy as the other lasers that we talked about, yet it's got a lot of advantages relative to the way that you can use it. So let's look at an example of this laser. The part you see on the screen has about a 150 millimeter depth measurement that it needed to be done. A laser measurement down at the bottom of this part. Let's play this video. So if you look real close where the arrow is pointing, this is the part. It cuts out the part just so you can see the depth that it has to scan at. And it's measuring a step height right there around that slot, kind of scanning around the contour of that radial slot and getting a lot of Z information out of that, the flatness, the location of that Z surface. But the interesting point here is that you don't even see the optics. You don't even see the laser. That's because of that large working distance that we were talking about earlier. Another non-contact sensor that is sometimes referred to a laser but isn't actually a laser. It's a white light sensor, but it acts the same way as a laser measurement. It projects white light down onto the part, and what it uses is the principle of chromatic dispersion. So the white light is sent down to the part, and what is received back is these different frequencies of light, and depending on how far those different frequencies of light are apart, that determines the distance from the part. So that graphic up on top, basically the green frequency is getting returned and the others aren't. So that's how we determine the height of that. Interesting technology, but it's very accurate, down to the nanometer kind of resolution. So, it does have a very typically short working distance, but for some applications that require a very high level of accuracy, it fits the bill perfectly. Some of those applications might be thin films or adhesives, lenses, those kinds of things. Once the signal is received back, a spectrometer is used to decode the images on a CCD array, and that's how it determines those frequency changes. Let's take a quick look at that one. This is called a rainbow probe that we use here. It's a white light sensor, so you don't see the actual spot on the surface, but it is scanning this lens. That black post there is actually the rainbow probe scanning over that surface and getting very high resolution on that aspheric lens surface. And then at the end of a three-dimensional scan on that, you might see something like this, where you're getting down to the color map of a surface and down into the micron level. Okay, and a little bit outside of the measurement range, but a useful tool is a thermal sensor. It is a sensor detecting temperature, and relative to the medical community, it's particularly interesting because a lot of the medical parts that go into the body are made out of such materials that are intentionally adjust to the body temperature, and the form and the shape and the size of the part is ideally matched for the body temperature. So it's an interesting challenge that manufacturers have for trying to control the manufacturing and the measurement of such parts that have such a quick response to temperature change. So what's been done is you take a thermal sensor and add it onto a multi-sensing system, and this thermal sensor is receiving the thermal effect back from the part, and determining the temperature of the part. So on these very thermally sensitive parts, you can have it monitor the temperature of the part and wait to do the measurement until it is at a temperature that's desired for the measurement. Or you can have it adjust the measurement for the temperature that it's at. So there's a lot of things you can do with thermal sensors to address some of these thermal challenges. So let's take a look at some of these things in action. This is an example of a multi-sensing system or a multi-sensing system measuring a medical device. So this is actually a bone plate, and it needs a video, touch probe, and laser to measure all the features. So here it's measuring the datum structure with video, measuring those two holes. You can see, if you look closely at the part, there's a red dot that's scanning around the surface of that plate down in the lower right corner. That red dot is the laser that's scanning over that contoured surface. Those laser data points are then going to be mapped onto a CAD model to determine any variation. Just went and picked up a touch probe, okay? This touch probe is necessary to get down into some of those holes and measure the diameter of those holes at a certain depth height. And so that, the advantage of a multi-sensing system is that you can take advantage of these strengths and weaknesses of the sensors. Here it's doing a laser scan around that kind of a spherical seating surface on that part. Which can only be done with laser because you're taking a lot of data points on a very small arc segment on that sphere, and that's a significant challenge. But if you have a lot of data points with the laser and a very accurate data points, then you're getting some good measurements out of it. So the strengths and the weaknesses of the sensors is really why a multi-sensing system is ideal, because each one has its strengths and each one has its weaknesses, but when you combine them all together, you get the best of all worlds, and it really is able to solve all the solutions with one system, which is the whole idea of this presentation. So we've talked about the sensors. Let's talk about the software solutions a little bit. Software solutions have to be able to support the sensors. They have to be able to maintain orientation and relationships between 3D features, control axes of motion, X, Y, Z axes, fourth and fifth axis rotation. They have to be able to program from CAD, fit to CAD, use GD&T, and then send out some reports that are meaningful to people who are making decisions on the measurements that we're taking. So those are all very software-related items that are key to making a measurement system functional. So relative to sensor support, it's got to be able to calibrate the sensor offsets. It's got to be able to put probes, and lasers and things on there and know that they're there and know how to react to them, know how to change the user interface so that it's easy to use, and also be, flexible so that it's one learning curve that you're going through when you're using. Doesn't matter whether you're using a video or touch probe or a laser sensor, it's all the same kinds of methods that you use to do it. You're just using a different tool to use it to make the measurement. And that, making that easy is key. Relative to fourth and fifth axis support, if you're sometimes a sensor is rotated to the part, so an articulating touch probe is something that you might know about, and that is rotating the sensor to the part. With a multi-sensing system, since some of these sensors you can't necessarily rotate, like a laser or the video, although there are techniques for doing that, but you may want to rotate the part in the fourth or the fifth axis to present the particular feature that you're measuring to the sensor in the most appropriate way. So the software has to have that integrity and be able to calibrate those axes out so that you're maintaining the micron level of accuracy. This is an example of a dual rotary application. This is another plate, very small, but it's got a lot of features at different orientations. And so what happens here is you are rotating one axis and rotating another axis to present those features to the measurement system. So here, just as a start, notice the probe orientation in the model window. And then as this does its different measurements, it's using video and touch probe to set up the datum structure here. And then it does a rotation. It actually did a rotation in both axes, a relatively large rotation on the primary axis and a small rotation on the secondary. And then so it used the touch probe to set up some datums. Now it's doing some laser scans, and those laser scans are relative to the datum that was set up. And so now it's rotating around to the opposite side of the part. So this sometimes eliminates multiple setups. Here it's doing a video measurement on some teeth the only way to measure that is with video. And the only way to measure it is to present it in that orientation. So it's critical to be able to rotate it and use the appropriate sensor there. So relative to CAD programming is important. So you bring a CAD model in and you want to use that to program from. So there's a couple reasons you might want to do this. You might want to do it to more easily navigate through the part, or to use the nominal and tolerance information of the part, and to gain some perspective as to what you're measuring and where you're probing when the model window is shown. But it also is good for offline programming. So if you don't have a part yet, and it's not actually a manufactured part, it's a designed part. You have a model, but we haven't manufactured it yet. You don't want to wait until the part's made to have a measurement program that can measure it. So you program the measurement program at the same time that you're manufacturing the part, then you're up and running as soon as the part comes down the line. The other reason for offline programming is to have the measurement system, if the measurement system is occupied in a production environment, you don't have to take it down to create the program. Fitting to CAD is another key software topic. So taking the data points that's acquired from all these sensors, the lasers, touch probes, all of those XYZ data points can be dropped onto a CAD model and fit appropriately to the GD&T tolerances, or to a least squares fit, and then you can do some engineering analysis. So if I change the way that this fit, or if I change the way the surface looks, is that going to improve am I going to make my part intolerance then? And then you can adjust your fixtures or your machine tools accordingly. So some tools there to help with both understanding what's happening to the part from a 3D perspective, and also feeding back information into the manufacturing process to improve it. And it's often overlooked, but reporting is a very important aspect of it. You need some clear, concise reports and understanding of what's happening, and sometimes those reports incorporate data relative to GD&T, which is the representation there. You see a stats plot, the statistical plot. If you're in a production environment measuring lots of parts, statistics might apply. And then you might have a report that has some validation and some electronic signature tracking, so that you're compliant with Part 11, FDA 21 CFR Part 11 and Part 820, with electronic signatures and audit trails and things like that. So it kind of depends on the kind of report that you want, but you do necessarily need to consider that, because that's how people make decisions. So let's look at one example of a pretty nice report. This one is more related to GD&T. So it's taking a CAD model, fitting the data onto it, and it's evaluating these different kinds of criteria that are necessary on this particular part. So there's different datum reference frames, different profile tolerances, different size tolerances. And depending on the kind of call-out that it is, sometimes it needs to move that data around differently to determine those things. So you get the angularity, the flatness call-outs, the profile tolerances, perpendicularity of B relative to A. This is a free-form surface profile relative to A and B. You get the color map of it. And then at the end you get a indication of failed or passed overall, and then within the different datum reference frames. Now those reports, what do you do with those reports? Well, you can print them out, you can send them out to different formats, you can email them. It really depends on the level of automation that you have and who's going to be looking at the reports. But all of those criteria need to be in there. Okay, so that's software. We've talked about compliance a little bit. Some of you might be more interested in this than others, but it's a necessary evil in some cases. But you have to make sure that the system and the programs and the whole system as a whole is compliant to all the requirements that you have to need or that you're subject to. So the first thing and the most important thing in my mind is the accuracy of the system. All these data points that you're getting out, they don't mean a thing unless that machine is accurate. And so you need to be able to calibrate and verify that machine to a high level of integrity. And so that's something that it's got to be considered. When you're talking about a multi-sensing system, the calibration and the verification of the sensors to themselves and to each other is critically important as well. And several patented techniques for understanding that and for really controlling that, which is something we've incorporated. Audit trail tracking, electronic signatures. If you are in an environment that's subject to FDA requirements, those kinds of things might be important to you. Also, relative to FDA Part 820, installation qualification, operational qualification, and production qualification. When you bring a new system into a plant that's subject to those requirements, then you have to have the people that are supplying these measurement systems have to have some knowledge of this so that they can help with services and provide recommendations on how to go through those IQ and OQs. So all that has to be considered. So let's first elaborate on accuracy a little bit. A 3-axis measurement system has 21 degrees of freedom. You have rotational errors, you have translational errors, you have squareness errors along each axis. So you have to be able to map that volume out, and you have to be able to verify that volume relative to standards like ISO 10360 is a standard out there for verifying the volume of a machine. And also algorithm certification. The software that's calculating the geometries has to be certified, and so that the calculations are correct. That's another issue. This is an example of a mapping of a CMM. So this is a relatively large horizontal arm CMM. This particular thing that's going on here is called an etalon tracer, and it uses it tracks the motion of the axis following this retroreflector that's mounted onto the end of that head. This can be used to calibrate CMMs, multi-sensing systems, machine tools, map out the volume of these things, and Etalon's done a very nice job at creating this tool and also the software associated with it. So here you're seeing discrete points being measured through that spatial diagonal, and then it's also done on the linear diagonal on the x-axis here. So those points are being measured relative to this laser measurement, so relative to known standard, in other words. So if those aren't measuring for what the machine is actually telling it's measuring, then it corrects for those errors by mapping out the volume. And so it goes through several iterations throughout to map the whole volume, and creates all of these different linear measurements, and then creates the map from that. It actually applies that 21 degree of freedom map to that whole volume. And on a large system like this, it can really help out. Smaller systems aren't subject to it, but smaller systems are subject to tighter accuracy requirements relative to the parts. In the end, you get a nice report with the envelope tolerance relative to the specification of the machine that you might be calibrating. Multi-sensor calibration. The sensors have to be calibrated to a standard and to themselves, and also to the other sensors around it. And there's several different techniques for doing this, but you have to make sure that that's those techniques are viable and well understood. Audit trail tracking, this is an example of an audit trail tracking the part through the measurement process so that you know who touched it, when they touched it, and you know how the part makes it through the manufacturing process. This is an example of another package that would, in a production environment, allow you to understand how to mount the part. So when you're talking about compliance, you want to make sure that it's a program that's measuring a part. You can have a list of parts that you select. You click on one of those parts. You see how to set it up with a text file. You might see an image of how the fixture looks so that you know where it goes on the stage and where the parts are laid out. And there might even be a movie that shows you how to seat those parts in the fixture. So you put that down, you clock it in, and so that all helps the user to put this information in correctly. This is showing you that you can, relative to compliance, typically you have to validate a program. So you might have a first article program that measures everything, and then you might pick just sub-features of that occasionally when you're doing, just critical features. So you can pick the features that you want to measure, and then it figures out what kind of datums to use in order to measure those critical features. And then the original validated routine isn't compromised because you're still using that same program. So it's a slick way of validating one program but using subsets of the program to get through it without revalidating. Here's an example of a report with some tracking information of who measured it, who reviewed it, who verified it, what the part number was, what the date timestamp was. All this information can be put into the report, and a lot of that is, so that we can maintain this compliance to 21 CFR 11. Installation qualification, operational qualification. There's services available. There's software that helps you become compliant. When you're talking about a system of this magnitude, you want to make sure that you can understand by, talking to the vendor that's supplying this, making sure they understand your requirements and working together on coming up with the best way of qualifying that part so that it doesn't take, 3 months to get the part machine up and running. You basically install it and you get it going. Okay, so that's basically what we're talking about. So how does this affect the bottom line? How does it save us money when you're talking about a multi-sensing measurement system? Well, there's several ways. Probably the most obvious is when you talk about a single equipment purchase versus several purchases. So this is a funnel of all these different measurement devices going down into one multi-sensing system. Okay, and then at the end of the day, it's saving you money because you don't have to buy all of these other more specific types of systems. You have one system that does it all. So that's the most obvious way that you can save money. But there are several less obvious ways that you can save money as well. By having one machine, you basically have one fixture setup. You have one measurement process. So when you're talking about lean manufacturing, you have all these different stages to do different measurements from. It's going to take, an extended amount of time, extended amount of people, extended amount of equipment. Okay, so you have one measurement process. You stage it up once, and actually that's minor too because the measurement system will actually find the parts for you. Basically taking these 4 stages in this example down to one stage to where while it's doing its measurement, somebody can be doing something else. This is an example of a multiple pallet frame with multiple parts on it. So something that you can put down onto a machine and it just runs through the parts and you just tell it the offset of the fixtures. So less programming time, less training, so you only have one training learning curve. Fewer calibration requirements, which can get expensive. We have a lot of measurement systems. Less part handling, so less damage of parts, less scrap, and all of this here is relative to higher productivity. So there's a lot of advantages relative to the bottom line on a multi-sensing system. into another one here. If you look at all of these sensors that we've talked about, each one has its own strength. So when you have all the sensors on a system, there's no compromises. You're gaining money because you have more capability in the measurement process. You know more about your parts because you're not restricted on the measurements. You get all of the information to make very good decisions. And if you don't have all the information, sometimes those decisions aren't appropriate, and that's how you end up losing your shorts in some cases. So this is a funny picture. I always like to see it setting up a tent. You know, I have my own struggles with that, and but it's kind of simulating. When I put a new machine on the floor in a QA lab or something, I want to have it up and running right away. So you by having a multi-sensing system, you have one learning curve. People are getting up to speed on it quickly. These qualification services or CANs, they give you examples how to do it. And then the turnkey systems, you can get programming with it and have it up and running right when it's installed. So that's a lot of the initial cost of installing a machine you're saving by getting that up and running nice and quick. When you're talking about the software on a multi-sensing system, this is a hidden one that a lot of people don't catch, but it's a killer. It can really cost a lot of money if you have a software package that isn't measuring the part appropriately. So especially relative to GD&T, if you have a system that is not compliant to the standard that the part, the design intent of the part, then you have the potential of passing good parts and rejecting bad parts. So GD&T tolerance is intended to maximize the design intent while minimizing manufacturing and inspection costs. But a lot of times it doesn't do that. You have to be able to understand that and have the software that can do it correctly and give you the right information so that you're not doing scrapping bad parts or scrapping good parts and accepting bad parts. So what are tomorrow's manufacturing challenges? That's something you have to think about, and how can a multi-sensing system help you? What are tomorrow's tolerances? Are the tolerances getting tighter? You have to be prepared for the next big thing. Okay, you don't know what's coming out there, and you want to have that capability at hand so that you can measure it when it comes down the pipe. At the end of the day, you have to ask yourself, is my measurement system helping me with the bottom line? So that's the conclusion. As a transition into the Q&A session, I'd like to just have one more example here of a multi-sensing measurement system. So this one is actually using laser and video and a fourth axis to measure a very small, intricate part, which in most cases would be very difficult to measure by conventional means. So it just kind of carries home the message that we're trying to bring across here with this multi-sensing system saving you money. So with that, Melanie, I think we can go into a Q&A session.
Thank you very much, Tom. Thanks for your presentation. So we actually are going to extend our hour for 5 more minutes, just so we can answer some of the questions that went through that have been asked. If you're unable to stay for these last 5 minutes, don't worry. We will definitely send you a link so you can review the video, all the videos, as well as all of the slides, and also hear the Q&A and see what you are missing. So with that said, we'll go ahead with the first question. Why can't one sensor do all my measurements?
That's a good question. It's relative to the limitations of each sensor. So when you're talking about video, the limitation is that you can only measure what you can see with video. So if I'm trying to measure a vertical wall or something that's recessed under the part, I can't see it, so I can't measure it. Relative to touch probe, I can't measure where surfaces intersect because I can't actually, probe that location right where they're intersecting. So that's where video is helpful. And a laser measurement, scanning over and getting a full contour data points of a part would take forever with video or a touch probe system, but it takes seconds with a laser system. So you're gaining all of these benefits from the different sensors. If you're limited to one sensor, you may not be able to measure everything that you need to measure, or it may take you forever to measure it, or it may not be as accurate as you need it to be.
All right. So this is a three-part question. Do you need a special probe in order to scan? How do you do statistical reporting? And how is the CAD programming working?
Okay. Relative to scanning with a probe, you don't need a particular kinds of probes. You can have different sizes, different materials, different lengths, different orientations. So you're not really necessarily tied to that. There are standard probes out there of all different flexibilities that you can use to scan. The second question was related to SPC, correct?
The second question is, how do you do statistical reporting?
Okay. So as an automated measurement system is running, it basically is acquiring data on typically multiple parts that might be fixtured up or that you're measuring throughout the day. So it's recording that information into a database, and it's recording it into that statistical database, and you can see real-time plots as each part is being measured. And then at the end of the day, you have that database that you can do statistical reporting on, so you can do your X bar and R charts and whatnot to determine how in control your process is. And there was a third part?
Third part is, how is the CAD programming working?
CAD programming. So you bring in a 3D model or even a 2D model, a DXF model for video, or if you're working with other sensors, a 3D model is probably more appropriate. But you bring in that model from your CAD program, and then you use that model to program from. So if you are measuring a cylinder, you rotate that cylinder to where you see it, just like you would in the CAD program, and you pick the appropriate sensor that you want to measure, tell it where you want to measure on that cylinder, and then it goes and measures it. So it helps with navigation. It helps with knowing the nominals and tolerances of the parts, because the CAD program is ideally nominal. And so that's kind of how it works.
All right. Why is a long working distance important?
When you're talking about a multi-sensing system, you have several sensors that are on the system, and you might have fixturing or parts that are that have some or some height to them. So or some fixtures with some height to them. So maneuvering around the part and maneuvering around these fixtures becomes important. If you're very close to the part, then you have a higher risk of collision, basically, with either the part or the fixture. And when you have a touch probe that might be on the system, and then a laser might be on the system, you just got to be conscious of that. So it just makes it more flexible, because you can have because you can be more away from the part. And also, when you're talking about rotating the part, if that part has little extrusions sticking out from it, and you're rotating it, it might have, if you're not far enough away from the part, it could collide into the system. So all those things you got to consider.
Okay. Are the touch probes capable of force testing if I were measuring the force required to deflect a feature at a given distance?
That's a good question. There are tools that do that. Typically, the probes that are on a multi-sensing system aren't measuring the force that it takes to deflect a part, because typically you have to have some sort of sensor that's understanding how much you're deflecting the part and when to trigger that force reading. So typically that's done, by other means. But there probably are ways of doing it. It's just a matter of incorporating it, but it hasn't been a common requirement. Okay.
So we have time for one more question. Let's see. Can a multi-sensor system have all its sensors in place at once? What about those little fragile ones? Does the user have to touch each one to use it?
Very good question. A multi-sensing system can have most all of the sensors on at once. Typically, there's one kind of laser, and there might be 2 or 3 kinds of probes on the system, and maybe a video sensor, something like that, on a full multi-sensing system. But those very delicate ones are typically retracted into the housing of where the sensors live, or they're docked. So you saw the touch probes dock over onto the side of the machine, like a machine tool would dock a tool. So that's one way. And then, but like that feather probe with the resonance probe and the interposer, those can be retracted into the system by means of what we call deployment mechanisms. And so that either uses pneumatics or a motor to retract those sensors up and out of the way.
Okay, thank you very much for answering those questions. Thank you, ladies and gentlemen, for your time. It looks like that's all we have time for, but don't worry, because we have kept a log of all your questions that have come in. The staff will go ahead and try and answer them as quickly as possible, and we definitely will get back to you, as soon as we are able to answer your questions there. So before we close, Tom, do you have any, any last-minute words, anything else that you'd like to emphasize before we end this meeting?
No, I don't think so. I hope you all got some good information out of it. I think, relative to a multi-sensing system, there's a lot of advantages in the capability, and, what this presentation was concentrating on were the costs that are associated with it, which is particularly relevant in this kind of environment. So just keep that in mind as we go forward.
Thanks so much. So thank you, ladies and gentlemen, for your time. Please go ahead and stay tuned for an email. It's going to be coming from me. It's going to be containing instructions on how to download Tom's slides, and then I will also cover Tom's contact information in case you'd like to contact him directly. I'll make sure that you have his email address, so at least if you think of any questions, you can just forward it on to him, or you can send them to me, and I'm more than happy to forward it on. So on behalf of MD&M Webinars and our sponsor, Optical Gauging Products, thank you so much for joining us. We hope to see you at a future event. You may now disconnect from this meeting.